My name's Devin Colon. I'm the Group 3 reporter and leader for this experiment because Philip doesn't like me that much. The introduction to this is a par bomb. Excuse me? I'm sorry, questions? All right, cool. The par bomb calorimeter is used to measure the heat released by combustion in a chamber. The chamber is submerged in water. The water changes its temperature, and the change in temperature is measured. And then we use that to mathematically find out the thermal capacitance of the system. We want to become familiar with these operations using a bomb calorimeter. We're going to be able to determine a thermal capacitance of a calorimeter, and we want to determine the gross heat of combustion of a sample provided to us. Some of the theory that we have is the first law of thermodynamics. Heat is the equation of mass times the specific heat times the change in temperature. We can rearrange this and find the thermal capacitance, which is mass times specific heat, just by using the heat of combustion over top the difference in temperature. And you can see that right here. But when we do this, you have to make sure to account for the ignition wire in your system. It's not just the fuel. Here's an example of the bomb calorimeter. I think we've all done it, but we'll go through it real quick. You have your ignition wire lighting the sample inside of a metal container. You have pressure inlets and outlets. When you go to do this experiment, you're going to pump oxygen in and release it several times, trying to get as pure of a mixture of oxygen in there as you can for combustion. And then when you finish putting that together, you're going to drop the entire thing in an insulated bucket full of water. The water is what you're going to be measuring the temperature of. Your combustion happens in here, it heats up, that heat transfers to the water to change the temperature that you're measuring and using to find all these values. And you're going to use a surge stick to make sure that the temperature is evenly distributed throughout the water. So here's the results for the benzoic acid. We use the benzoic acid to figure out the thermal capacitance of the system itself, seeing as that we know the heat of combustion for that. Looking at the data, when you drop the bomb in, the water is X amount of temperature, but the bomb's a little bit different. So you have some time you give yourself before implosion to get a state of equilibrium in the system. And then once you explode the sample, that's when you have your temperature change in the water, and you want to figure out a spot where it levels off before it starts to go down, and that's the data you're going to use. So the final temperature we got for the benzoic acid was about 26 degrees Celsius, and the initial was about 24 degrees Celsius, with the initial being an average of these values. And when you work that out, along with accounting for the heat from the wire and combustion, you find that the system itself has a thermal capacitance of about 10.32 kilojoules per degree Celsius. So then you're going to move forward with your unknown sample, or a bag of gummy Skittles, very unknown. Using that value with the values you get from the same experiment with the Skittles, where you give yourself the time for the temperature to level out, implosion, and again to level out, and you're going to use the average of these two temperatures to run your math. And you end up getting a thermal capacitance of heat of combustion for the sample of 12.78 kilojoules. When you take into account the heat from the wire of the system, you get 12.72 kilojoules, and when you convert that to calories, you get 3.03 calories of that sample. So then when you look at your bag of Skittles, you see that it's 90 calories per 28 grams, and then we had a 0.99 gram sample of gummy Skittle ourselves that we combusted. So it should have been 3.18 calories. We got 3.03, which is about 4.7% of an error, but that's actually okay within the industry standard, so they can get away with that. Because I was for sure right there wrong. I was right. All right, so when we look at some of the samples from not just my experiment, but group 1 and group 2, you get an average for the colorimeter thermal capacitance of 10.99, and the standard deviation of that was relatively small. And a little review of standard deviations, if you go 3 either way, within those values should be about 99.7% accuracy, like, of it being good. So that was a decent right there. It was only 10.99 plus or minus 2.29. But when we got to the heat of combustion of the gummies, our samples varied fairly drastically. We we got a standard deviation of 3.28 for a total of 14.9 plus or minus 9.84, which is a very large range. I think that's going to be error in us weighing our samples. I think it's going to be error in maybe the gummy itself being slightly different, not as dense. There could be air pockets in the candy. And then here is some known values of heating pulled from Caleb's report, specifically from his report, but it's okay because I referenced him right here. Check the references. But you know, Skittles were kind of in line with dry wood, but with the plus and minus factor, I mean, it could be charcoal, either one. I mean, you could put wood, charcoal, you're trying to stay hot in the winter, just maybe throw some Skittle gummies in there, it's about the same thing. It doesn't matter, whichever one's cheaper, but that's it. That's their plan.